All right, so this lecture is going to be on the law of conservation of momentum. It's one of the most fundamental laws in physics, along with the law of conservation of energy. And so it's very similar to the law of conservation of energy in that there's a caveat in which momentum is conserved. And that caveat is that for a closed system, meaning there's no outside forces, then the momentum is always conserved. Okay? And this is such that the sum of all the initial momentum must be equal to the sum of all the final momentum. And the way we represent that in an equation is that the sum of all the initial momentum has to be equal to the sum of all of the final momentum. Okay? And momentum is conserved in all collisions. Like even when you have like really, really large objects, like if you look at the microscopic scale of the collision, momentum is still really conserved. So for example, like when we think about the idea of a bouncy ball, when we drop a bouncy ball and hits the ground, there's a collision that's occurring with the bouncy ball and the ground. And the bouncy ball jumps back up, but it doesn't go to its maximum height. And that's because some of its momentum was actually transferred to the ground. And we don't notice that because the ground doesn't really seem to change at all. But if you look at the microscopic level, the molecules in the ground are changing a little bit, like they are moving a little bit more, so maybe their velocity is increasing, which is causing a heat increase, etc. If you were to look at like a bigger scale and you were to drop a bowling ball in the ground and you put a dent in the bowling ball, the momentum transfer of the bowling ball goes into the momentum transfer of those molecules in the ground. So momentum is conserved in all collisions if we exclude outside forces, meaning right after the collision, we see that momentum conservation. Now clearly if the objects collide and then one object moves along and it's slowed due to friction, well that's a different part of the problem. But if we look at just purely the collision involved, momentum will be conserved. So whatever total momentum I start with has to be equal with the momentum that I end with. And we are going to focus on collisions, and there's two types of collisions that we are going to look at. The majority of collisions that we see in everyday life are called inelastic collisions. So most of the collisions that we see are inelastic collisions, and these are collisions where only momentum is conserved. Kinetic energy is lost in the form of heat in these types of collisions. So in the form of heat or sound, energy is leaving our system due to the collision. Okay? So if only momentum is conserved, we still have this idea that let's go initial. Initial momentum is equal to final momentum. Kind of how that plays out. Let's say you have two objects and they're both moving to begin with. Always lose the gap. You could say that the initial momentum of car 1, we'll go 1 initial, plus the momentum of car 2 to begin with. So this is M1 V1 initial plus M2 V2 initial. That's my initial momentum. So if I could kind of here, that's my initial momentum, the sum of my initial momentum, and that has to be equal to the sum of my final momentum. So it would be M2 V2, let's start with ones, M1 V1 final plus M2 V2 final, and that would be my sum of my final momentum. So this is kind of the general format that we're going to see for conservation momentum, where this is my initial momentum, this is my final momentum, and the sums should be equal. So individual momentums are not necessarily equal to each other, but the sums are equal to each other. Now there's one kind of inelastic collision that is special, and it is called a completely inelastic collision. And with a completely inelastic collision, this is when the two objects stick together after the collision. So completely inelastic collision, the two objects stick together after the collision, and so the equation actually is a little different in the sense that we're still going to have M1V1 initial plus M2V2 initial, but then over here on my final side, because they stick together, they're going to move off with a combined final velocity. So the equation actually becomes a little bit simpler because there's only one final velocity on the end. Okay? So that's a completely inelastic collision. They stick together afterwards. The second type of collision that we can look at is what's called elastic collision. And elastic collisions are definitely very simplistic. Not simplistic. They're very specialized problems. In fact, they happen here in whiteboard land, they happen in your textbook, they happen at the atomic level, okay? But in real world, these don't happen unless we help make them happen. Because with elastic collisions, during the collision, momentum and kinetic energy are conserved. And so these are very idealistic cases. This assumes no energy loss to heat or sound. So in this one, the sum of my initial momentum is equal to the sum of my final momentum, and I have this additional restraint that the sum of my initial kinetic energy is equal to the sum of my final kinetic energy. So later on, I will model a problem for an elastic collision, and we're going to see that there's another equation that kind of helps us out, but we have to go through the derivation, and that's going to be just its own separate video, so you can watch it over and over and over again until you get it. But there's those two types of collisions. Inelastic, which are the majority of the collisions we see in everyday life, and then there's elastic collisions, which happen when there is no friction, we don't lose any energy to heat, any energy to sound. It's very idealistic, but if the problem specifies that it's an elastic condition, then you can follow these parameters, that the momentum is conserved and kinetic energy is conserved. The other thing I want to talk about before we actually go through an example of momentum is just how to solve momentum problems. And like, what's our general strategy? I know with forces, our general strategy was to always just draw the force diagram and then we'd write out our force equations. So we're going to have a similar strategy anytime something collides or explodes. Okay, so this is going to be something colliding or exploding. When that happens, your first instinct should be, can I use momentum to solve this kind of a problem? So with this, you really need to draw before and after pictures. And look at what is moving to begin with. What has momentum to begin with? What has momentum afterwards? And then set those things equal to each other. And then just like we would write out our force equations, we're going to write out the momentum equations. So this is going to be that our initial momentum is equal to our final momentum, and then you're just going to solve. But this first step, the drawing, it's key, and you should have known that from the force chapter. Drawings are key. If you don't have a good drawing, you're not going to have a good set of equations. The same thing is going to happen with momentum. If you do not have a good drawing, you're not going to know what has momentum before, what has momentum afterwards, and then how to set them equal to each other. Okay? Now, one of the kinds of problems that you might encounter is what happens if there's no initial momentum. And this usually happens for explosions. This happens when you have two people that are initially stationary and then they push off of each other. Okay? So essentially, nothing is moving to begin with. And if nothing is moving to begin with, then the initial momentum has to be equal to 0. But if conservation holds true, then the final momentum has to also be equal to 0. And so the result is that you're most likely going to have m1v1 final plus m2v2 final equaling 0. You're going to have, if you only have two objects, you're going to have these momentums ending up equal to each other. Okay? And you could solve for it that way.